Okay, so, we are looking at description logics, and we are looking at one particular description logic, uh, which is has these concept forming operators, which says that all are D, which says that all role fillers belong to the class D. So, class and concept we will use interchangeably. Then exists n R, which says that all it must have at least n individuals it is related to by the role R. Then fills are A, where if A is a constant, that it must be related. So, this is a set of all those individuals which are related by role R to A, and then and d 1 up to d n, which means that it must belong to all those classes d 1, d 2, d 3. And so, if you want to say that somebody is a female surgeon, and if you say that a surgeon is a doctor with specialty surgery, then you have to say and female doctor specialty surgery. So, if you say all these three things, you have in effect defined a female surgeon. So, let us look at an example here. So, very often we use compound definitions to define some named concepts. So, if I want to define a company called a progressive company, then I can define it by listing out all the features of that particular company. So, it is a little bit like frames in that sense, that you are saying these are the properties and these are the values, or these are the attributes and these are the fillers, though it is not only in terms of that, we are defining in terms of this particular concept forming operators. So, remember that this sign that we have looking at, it basically says that two concepts are equivalent. So, on the left hand side we are giving this name of a new concept, we are giving a name to a new concept, and on the right hand side we are defining that concept essentially. So, we can define it by saying that all these things must be true, that first of all that it must be a company. Let us say company is a concept, and then it must have at least 7 directors, and then we can say that all its directors are female, which is a class, and who have a degree, which is a relation PhD, which is a individual. And whose mean salary that they offer is, let us say, in some denomination 100,000. So, this is a class or a concept that we are defining. It is a set of individuals which we will call as progressive company. So, we are individuals in the sense that they are something in the domain, some concept that we are defining in the domain, which are basically companies who have at least 7 directors, and all whose directors are female with PhD degrees, and who at least give 100,000 to. So, min salary is not only for the directors, it is for everybody else essentially. So, if it was for the directors, then it would have been part of all directors have min salary 100,000. This is outside of that. So, which means that is the minimum salary that the company offers to anyone is 100,000. So, if you are given this description and if you are given another description, let us say I have a concept called, which we will define shortly, high tech balanced company, which I have not defined yet, but we will do it in a little while. The kind of questions that we want to ask are that is one set. So, remember, these are sentences we are talking about here. So, this is a sentence in our language, and the sentence says that essentially in terms of first order logic, you are saying that all high tech balanced companies are progressive companies essentially. Is this sentence true or not? Does the knowledge base entail this sentence? And we will say that yes, if the interpretation of high tech balanced company is a subset of the interpretation of progressive company. So, that is a notion of entailment in this language essentially, that this statement that high tech balanced company is a type of progressive company would be true if the mapping of this concept of high tech balanced company were to be a subset of the mapping of the progressive company. Now, that is only the semantics essentially, but if you want to answer this question. So, just as in first order logic we do not use the semantics to answer questions, we only use it to clarify as to what is it that we are trying to do. Here also we are simply saying that this is what we mean by this thing. We have to have a procedure for doing it essentially. So, we are moving towards a procedure for computing subsumption. And we will see later that once you know how to compute subsumption, then the other questions, whether a company, whether two concepts are equivalent or whether an individual belongs to a concept, can be answered quite easily. So, the key question is, can you compute this, that is a concept D subsumed by a concept E, is this a true statement or not essentially. So, we want a procedure for doing that essentially. So, we start by a process called normalization. Of concepts. So, in our case we will normalize these concepts and translate this question to is D prime subsumed by E prime, where both these are normalized, and we are looking at the process of normalization now. And we will see that once you normalize concepts in this particular language, at least simply by looking at the two concepts you can answer this question by yes or no, which means that the complexity of answering this question is only going to depend upon the size of these two formulas essentially, or the size of the two normalized formulas essentially. you do not have to do any other kind of reasoning to answer this question essentially. So, let us look at this process of normalization. So, initially you first ignore statements of the kind individuals belonging to concepts. Because we have said that we are only going to focus on subsumption for the moment essentially. Then you ensure that every compound concept has one definition. Which basically means that if this is a compound concept D, then there is one definition and it has got something in it essentially. So, it occurs exactly once on the left hand side of a set of statements like this, and you can always do that, because if you have D is equal to some, let us say, and E and F, and there is another statement which is and G and H, you can always combine them to say and E, F, G, H. So, you have one definition for every concept, and then we will assume, or you sort out your knowledge base, that there are no circular definitions. What do you mean by this? That if you define a concept D, for example, in terms of E, so and E somewhere, and then you define E in terms of some concept F, then you do not end up defining F in terms of D, for example. So, we are saying that this is not allowed. It is not disallowed by the semantics, because in semantics you can always define concepts in a circular fashion. You can always say that a child and parent is a circular relationship, that if X is a child of Y, then Y is a parent of X. But just for the sake of simplicity and for the sake of the algorithm that we are looking at, we do not want to have this kind of circular definitions. And the motivation is that when we are going to normalize these concepts, we are going to have only those names of concepts which are not defined in terms of other names essentially, because that will allow us this process of inspecting these two formulas in a simple fashion essentially. Okay, so, we look at this process of normalization. So, the first step is expand definitions. So, if there is a concept, if there is a statement which says D in terms of, let us say, and something something, then you want to replace in, let us say, another concept F is equal to and something something D. So, let us say this is and G and H and nothing else, where G and H are concepts, to give you F is equal to and whatever it was, but replace this D by and G and H. Which means that eventually on the right hand side there will be no compound concepts, only what you can call as atomic concepts. Atomic concepts are those concepts which are not defined in terms of other concepts essentially. So, on the right hand side you will have only atomic concepts essentially. Then the next step is to flatten AND operators. So, you can see that if I take the example that I have just used, supposing this was something like this and some concept D 1, D 2 and G H and let us say I J, then what are you saying, that this concept F is a subconcept of D 1, it is a subconcept of D 2, it is a subconcept of G and H. So, this concept says that it is a subconcept of G and H, it is the intersection of the images of G and H. This says that it is the intersection of images I and J essentially. So, essentially you want to remove this and replace it with by D 1, D 2, G, H, I, J. So, remove unnecessary AND operators from this thing. Then the next step is to combine all operators where you can, so that if you have a concept, for example, and let us say all row fillers are D and somewhere down the line you have all row fillers are F or let us say G. For example, this could say that somewhere you are saying that all its children are doctors and somewhere else you are saying that all its children are tall or something like that essentially, or musicians or something like that. Then you replace it by all R and D. So, basically there is only one occurrence of all R of some concept class and you have combined those concept classes of D and G here into this whole thing here. So, they were occurring in separate AND statements, so now they are occurring in one common AND statement. Then the next step is to combine exist operators. Which says that if you have a statement of this kind and then replace it by a single exist statement let us say P R, where what should P be? Max of n and m. So, for example, if somewhere you have said that amongst the other properties of this set that we are defining, it has at least let us say 2 bank accounts, and somewhere else you are saying they have at least 3 bank accounts, then you this 2 bank accounts is kind of redundant, because in the other place you are saying that there are at least 3 bank accounts. So, you just need to keep only this. So, in this example, whichever is the maximum of n and m, you will bring here, and the other one you will just throw away. Then deal with thing. Okay, so, I have not spoken about what is thing. Thing is a concept such that the image of this concept is equal to the domain D. There are some books which use top and bottom here, but we will use the term thing essentially. So, likewise there is the nothing which stands for the empty set essentially. So, thing stands for the entire domain and nothing stands for the empty set. So, if you have a statement of the kind and somewhere you say thing, or maybe somewhere you say all or thing, then you can see that this is not really doing anything to the description, because all you are saying is that it is in the domain essentially, because everybody has every individual has to be in the domain, because these are true statements. C concept thing, this is always true, and A belongs to thing is also always true. So, a thing basically does not contribute to anything. So, whatever this is not adding to any description of this concept that we are trying to describe. So, you can just throw it away. Likewise, this is also not adding anything to the description, because you are saying that all role fillers must be of the type thing. So, obviously, they have to be of the type thing, because everything belongs to thing in any case. So, you just throw it away essentially. And finally, simplify. It basically means remove duplicates, if any, at any point. So, let us look at an example. We start with a company called a well rounded company, which is defined as a company in which all its managers what did we do in the last time? We said all managers. Yeah. Or did I say directors in the last time? Directors. So, let me use directors. So, a well rounded company is a company all whose directors are B school graduates and who have at least one technical degree essentially. And let us say there is a company called high tech company, which is also a company and which is listed, let us say, on this American exchange NASDAQ, and all managers or directors are techies. And then we define techies as saying all those people who have at least 2 technical degrees essentially. Now, if you want to define a new company called let us say well rounded high tech company. So, I am not writing the full name, it is a company that I was trying to define earlier, is defined by saying and well rounded company, these are all one words, and high tech company. So, supposing I define this and then I need to normalize this. So, if you remember, we had defined this notion of progressive companies sometime, and if you want to ask a question whether a well rounded company is a progressive company or vice versa, then you first need to normalize these things essentially. Okay. So, we have just gone through this process of normalization. So, I will just do this very quickly on this sheet here and expect you to do this in a little bit more detail later essentially. So, the first thing we will do is that we will replace this by this definition. So, this will go here, because we want to use only atomic concepts. So, the only atomic concepts are company and things like that. Then what will we get? We will get all directors have at least 2 technical degrees essentially. Then we will combine all this whole thing into one definition. We will flatten these ands. So, all these ands will go away from there. Then we will combine this all directors with all directors here, which means this will go and this will come here, this 2 tech company. Now, when we are combining this all directors, so we will say all directors have to be B school grads and they have to have at least 2 technical degrees. So, this will remain, this will remain, this will go away, because the way we combine this exists. So, all directors will become and B school grads and exist tech companies, and the company fills NASDAQ, and because there is redundancy here, we will throw away this one company from here. So, finally, what will remain is that a well rounded high tech company is a company whose all directors are B school graduates with at least 2 technical degrees now, because we have to combine both the things, and which is listed on NASDAQ essentially. And the claim that we are making is that with this normalized form of definition, we can take another normalized definition, and simply by looking at the two definitions we can say whether one is subsumed by the other, and we will do that in the next class actually.